try to solve this problem. Try to solve this problem. Mechanism is something like this. So try to find degrees of freedom for this mechanism. This is a single link, okay? So whenever you come across these kind of arrangements, the link is continuous in the hinge. It indicates that it is a single link, okay? It's a single link. Yeah, find degrees of freedom for this mechanism. So I'm counting number of links. This is fixed link, link number 1. So this is link number 2, this is link number 3, this is link number 4, and this is link number 5. So there are 5 links, okay? So number of links are 5. Number of links are 5. If you see number of lower pairs, this is a turning pair, 2, 3, 4, 5, 6. Number of turning pairs are 6, turning pairs are lower pairs. If you see number of higher pairs inside the mechanism, there are no higher pairs. So try to find out degrees of freedom for this mechanism. Degrees of freedom is 3 into n minus 1, so minus 2 times lower minus higher, 3 into n minus 1, minus 2 times number of lower pairs. So if you try to find out degrees of freedom for this mechanism, degrees of freedom is 0, okay? Degrees of freedom is 0, and if you look at the mechanism, so even when you try to move these links, you cannot move these links, okay? So when I try to rotate this link number 2, I cannot rotate link number 2 because this link number 3 is very long and it's, so because of link number 3, so this restriction is prevented, I mean this rotation is prevented, okay? So rotation of link 2 is prevented because of the length of link 3. Link 3 is very long, okay? So degrees of freedom is 0, okay? You cannot move anything in this mechanism. You cannot move anything in this mechanism. So try to calculate degrees of freedom for this mechanism. So try to find this degrees of freedom. This mechanism is called as a double parallelogram mechanism, okay? These 3 links are of same length. These 3 links are of same length, okay? So try to calculate degrees of freedom for this mechanism. So here degrees of freedom is 0, okay, in this case. Here degrees of freedom is 0. Let's look at this mechanism. So if I count number of links inside this mechanism, this is link number 1, fixed link. This is link number 2, this is link number 3, this is link number 4, this is link number 5. Number of links inside this mechanism are 5. And if you find number of lower pairs are 3 here and 3 there. Total number of lower pairs are 6. There are no higher pairs inside this mechanism. So this is very similar to the previous case. Number of links are 5, number of lower pairs are 6. No higher pairs. If I try to calculate degrees of freedom for this mechanism, this is 3 into, so n minus 1. 3 into n minus 1, so minus 2 times number of lower pairs, number of higher pairs. If you try to calculate degrees of freedom for this mechanism, so as per Kutzbach's criterion gives a result of 0, okay? Kutzbach's criterion gives a result of 0, but if you observe the mechanism, if you look at the mechanism, whenever I say degrees of freedom is 0, there should not be any kind of relative motion between the links. So, but here, try to imagine this, when I rotate this link number 2, link number 3 rotates, and link number 4 also rotates. Here I have relative motion. The relative motion, or I can say here there is, I can give one input here and I will be getting only one output here exactly. So I can say degrees of freedom for this mechanism is 1. So but as per Kutzbach's criterion you are getting degrees of freedom is 0. So I can say the result what you are getting here is incorrect. So Kutzbach's criterion gives incorrect results in some situations, okay? So yesterday we have seen what are the drawbacks of Kutzbach's criterion. So Kutzbach's criterion, if you see, this is Kutzbach's criterion, this formula. For calculating the degrees of freedom, he considered number of links, number of lower pairs and number of higher pairs, but he didn't consider the geometry of these links. So this is the drawback of Kutzbach's criterion. So in this case, the number of links are 5 and number of lower pairs are 6. There is no relative motion because length of this link is very long in comparison with length of the other 2 links. Here degrees of freedom is 0, this is correct, but here it is wrong, okay? So this is one kind of situation where Kutzbach's criterion fails. There is one more kind of situation where Kutzbach's criterion fails, okay? So there are 2 different situations where Kutzbach's criterion will give incorrect results, okay? We'll discuss the 2 cases. Let's write down like this. Let's write down like this. Kutzbach's criterion for degrees of freedom of planar mechanisms, Kurzbach's criterion for degrees of freedom of planar mechanisms gives incorrect results or fails in few cases. Kurzbach's criterion for degrees of freedom of planar mechanisms fails in few cases. Fails in few cases. This is due to the reason that length of links and other geometrical properties are not considered. Length of links and other geometrical properties are not considered for calculating degrees of freedom. In Kurzbach's criterion. Okay. So there are two cases where this Kurzbach's criterion gives incorrect results. So right on the first case, case one, a redundant link. This is first case, okay? So whenever there is a redundant link inside the mechanism, Kurzbach's criterion will give incorrect results, okay? Whenever there is a redundant link. And what is redundant link? You can see the name itself. It's redundant, okay? It's redundant. So every link inside the mechanism should introduce some kind of restrictions or some constraints in the motion of the mechanism, okay? So sometimes there will be some links which do not introduce any restrictions or constraints inside the system. So there is no use of such kind of links, you can eliminate them, okay? So even if their presence and their absence doesn't make any difference in relative motion between number of links, so those links can be eliminated, okay? Those links we call them as redundant links. So redundant links are those links which can be eliminated. So even after eliminating those links, the functioning of the mechanism will remain the same, it will not change. If you look at this mechanism, in this mechanism, every link is introducing some constraints, okay? Every link is introducing some restriction. If you remove any one of the links, so the functioning of the mechanism will entirely change. Now in this case, there are 5 links. When I try to rotate this link number 2, I cannot rotate it because this link is very long, right? I cannot rotate it because of link 3, everything is getting jammed. Now what you can do is, you try to eliminate any one of these 5 links. If you try to eliminate any one of these 5 links, if I eliminate link number 2, what happens? If you eliminate link number 2, you can easily rotate link number 3. When you rotate link number 3, link number 4 also rotates. So I can say link number 2 is introducing some constraints, okay? So link number 2 is not a redundant link here. You take any other link, you try to eliminate link number 4 or link number 3, you eliminate any link, even if you try to eliminate link number 3, the functioning of the mechanism will change. You can rotate this link and this link. So if you try to eliminate link number 4, link number 5, it's exactly the same as eliminating link number 2. Try to eliminate link number 5, so entirely everything is going to change. So I can say in that mechanism, every link is introducing some constraints, okay? Every link is introducing some constraints. So the mechanism, the functioning of the mechanism is defined only by the presence of all those links. If you eliminate any one link, the functioning of the mechanism will change. Whereas in this case, if you see, you try to eliminate any one of these 3 links. So the input is rotation and the output is also rotation. So input link is rotating and output link is rotating. Basically both the links are rotating. You try to eliminate one of these 3 links. If I try to eliminate this link number 2, I will give the input here and I will take the output there. The functioning of the mechanism is exactly the same. It didn't change. So I keep 2 and I try to eliminate link number 3. When I eliminate link number 3, I can rotate link number 2 and I can rotate link number 4. So you can keep link number 3 and you try to eliminate link number 4, then I can rotate these 2 links. So you try to eliminate any one of these 2 links, these 3 links, the functioning is not getting affected, okay? The functioning is not getting affected, but if you try to eliminate 2 links, so I'm eliminating link number 3 and I'm eliminating one more link, it can be any one of this. If I try to eliminate this, when you eliminate 2 links, now you can see the functioning is entirely different. Okay. So whenever I say redundant link, so redundant link is that link inside the mechanism which is not introducing any extra constraints inside the system. So those links can be eliminated. Even after eliminating those links, the functioning of the mechanism will not be affected. Okay. So if you want to find out how many redundant links are there inside the mechanism, you try to eliminate So you just observe the mechanism. So by observing the mechanism, you will get an idea whether there is any redundant link or not. So if you have any doubt, you just try to eliminate that and you try to visualize with the remaining number of links. If the functioning is not changed, so that is a redundant link. If the functioning is getting affected when you eliminate any one of the links inside the mechanism, that's not a redundant link. Okay? So in this case, there are no redundant links, okay? In this case, there are no redundant links. No redundant links. No redundant links. Whereas in this case, there is only one redundant link. You can eliminate only one among these three links. 2, 3 and 4. Only one link among these three links. If you eliminate two links, so then the functioning is getting affected in this case. Okay? Just write down like this, redundant link. Redundant link. What is redundant link? Write down redundant link. Sometimes a mechanism may have one or more links. A mechanism may have one or more links which can be eliminated, or just write down like this. Sometimes a mechanism may have one or more links which do not introduce any extra constraints into the system. Which do not introduce any extra constraints or restrictions, whatever it is. Which do not introduce any extra constraints into the system. Which do not introduce any extra constraints into the system. Such links are known as redundant links. Such links are known as redundant links and should not be counted for calculating degrees of freedom. And should not be counted for calculating degrees of freedom. Let's take down this diagram. Take down this example. Just write down like this. In the above mechanism, there are 5 links. In the above mechanism, there are 5 links with 6 turning pairs. There are 5 links with 6 turning pairs. In the above mechanism, there are 5 links with 6 turning pairs. The functioning of the mechanism will not get affected. The functioning of the mechanism will not get affected even when one of the links of 2, 3, 4, even if one of the links of 2, 3, 4 is eliminated. Even if one of the links of 2, 3, 4 is eliminated. Okay? Thus, effective number of links are only 4. Effective number of links are only 4. So one among these 3 links is a redundant link, okay? You can eliminate any one link, so I'm eliminating link number 3. So after eliminating link number 3 or one redundant link, you try to find out how many effective number of links are there, effective number of lower pairs are there. So effective number of turning pairs in the sense, so this is one turning pair, second turning pair, third turning pair, fourth turning pair. There are 4 turning pairs, okay? Whenever you calculate turning pairs in the sense 2 links are connected, okay? Here 1 and 4 are connected by a joint. You have to count only these joints. Here nothing is connected, okay? So you should not consider these 2, okay? You should not consider these 2. Effective number of links are only 4 with 4 turning pairs, no higher pairs inside the mechanism. If you try to find out degrees of freedom for this mechanism, 3 into n minus 1, so minus 2 times number of lower pairs. Degrees of freedom for this is 1. So you should get degrees of freedom as 1, and if you follow Kutzbach's criterion, you will get degrees of freedom as 0. Whatever the result that you get by Kutzbach's criterion, it is wrong. So because there is a redundant link inside the system. Yeah. So whenever there is a redundant link, you try to eliminate that link and you calculate effective number of links, effective number of lower pairs, and then calculate degrees of freedom, okay? So redundant link is that link which can be eliminated. Even after eliminating that link, the functioning of the mechanism should not get affected. Okay? hope you understood what is redundant link. So try to find out degrees of freedom for this kinematic chain. It's a little difficult, but so most probably you will be given simple mechanisms, okay? Only simple mechanisms you can visualize. If the mechanism is too complex, then it's a little difficult to visualize, then you have to practically deal with the mechanism, okay? You have to make a construction of that and then you have to deal with it. Most probably you will be given simple mechanisms, okay? So it's difficult for anyone to identify degrees of freedom for any complex mechanism just by looking at it. So here there is no redundant link, okay? So if I eliminate this link, what happens is you can rotate 360 degrees link 3 and link 4. Okay? So this is not a redundant link, I cannot eliminate this. So if I eliminate link number 3, then it's perfectly a parallelogram mechanism. You can rotate this and you can rotate this. Both the links will rotate 360 degrees. So if you eliminate link number 4, then 2 and 3 will rotate 360. They don't rotate 360 degrees, but they will be having an angular oscillation. So the function will get affected, okay? Yeah, it's a kinematic chain. No link is fixed, right? If no link is fixed, it's a kinematic chain, okay? So degrees of freedom is 2, okay? You will get degrees of freedom as 2. Yesterday we discussed the minimum number of degrees of freedom for any kinematic chain. So what's the minimum number of degrees of freedom for any kinematic chain? What is the minimum number of degrees of freedom for a kinematic chain? So I told you yesterday I can move the entire kinematic chain in x direction, I can move the entire kinematic chain in y direction, and I can rotate it about z axis. Okay? So you will be having 3 degrees of freedom, okay? So the entire chain can be moved in x direction, it can be moved in y direction, and it can be rotated about z axis. Those are the 3 degrees of freedom, and internally inside the kinematic chain you may have some more degrees of freedom. So yesterday we have solved one problem for calculating degrees of freedom for a kinematic chain. So we got degrees of freedom as 5. I told 3 degrees of freedom is the combined chain can move in 3 possible directions, and the remaining 2 degrees of freedom is inside that chain you can have 2 possible arrangements of links. Okay. So for a kinematic chain, minimum degrees of freedom should be 3, okay? But for this case, if you try to calculate degrees of freedom, you will get degrees of freedom as 2, so it's wrong answer, okay? It's not correct. Your Kurzbach's criterion is giving incorrect results. It's giving incorrect results. It's giving incorrect results. Why it's giving incorrect results? Because there is a redundant link inside this kinematic chain. If you look at this kinematic chain, there is no relative motion between these links, okay? There is no relative motion between these links. Whenever there is no motion inside the kinematic chain, that kind of chain is called as a locked chain. This is a locked chain, okay? As a locked chain, if you look at this kinematic chain, there are 1, 2, 3 and 4 links. There are 4 links. So if you look at this kinematic chain, even if I eliminate one of these 2 links, so if I eliminate this link number 3, earlier there was no relative motion between the number of links. Even if you eliminate link number 3, there is no relative motion, okay? Even after eliminating 3, you don't have any relative motion between links. So you keep link number 3 and you try to eliminate link number 4. When you try to eliminate it, now also there is no relative motion. So I can eliminate only one link among 3 and 4, okay? So even if you eliminate one of these 2 links, 3 or 4, the function is not getting affected. But if you eliminate both the links, if I eliminate link 3 and link 4, then the function will get affected. Or if I eliminate any one of these 2 links, the function will get affected. So I can say only one among these 2 links is acting as a redundant link. Okay? Number of redundant links are 1 here. So what you do is you eliminate one of these links. So after eliminating one of the links, you calculate the effective number of links and effective number of lower pairs. So this is 1 lower pair, 2nd lower pair and 3rd lower pair. Effective number of lower pairs are 3, so no higher pairs. You calculate degrees of freedom for this kinematic chain. 3 into n, so minus 2 times lower. 3 into n minus 2 times. So degrees of freedom for this kinematic chain is 3. You should get that as 3, okay? You get it as 2, but the reason why you are getting 2 is you didn't consider geometry of links. Is this clear? Redundant link. So redundant link is a link which can be eliminated. So even after eliminating that link, the function will not get affected. It's remaining, okay? It's pending, I can say. We have not reached till that topic. Maybe after 1 hour you will get to know the answer for it, okay? Yeah, the 3 degrees of freedom for the chain are, I can move this entire chain in x direction, I can move this entire chain in y direction, I can rotate the chain about z axis. Those are the 3 degrees of freedom. Yeah, Kumar, it's a little difficult to identify redundant links in complicated mechanisms, okay? So in our course, we just have 4-bar mechanisms, okay? Mostly you'll be getting questions from 4-bar or 5-bar, not more than that. Okay? If number of links are more, so then it's a little difficult to identify redundancy. Not only for you, for everyone, okay? Next item, this is one case where Kutzbach's criterion fails, okay? Whenever there is a redundant link. Next item, second case. Yeah, so that you can do, but so whatever may be the method that you are following, so that can be used only for the mechanisms which are simple, okay? If there is any complex mechanism with more than 8 or 10 links, so in such cases it is a little difficult to identify. So you have to practically see the mechanism, okay? So unless you see the mechanism and you try to work on it, you cannot identify the redundant links, okay? Then it will become a practical question. If number of links are less, then it's easy to visualize, okay? So from there we can identify them. So in other ways, you have to do the same thing for each and every link. So if you do for each and every link in a complex mechanism, it takes time. So you don't get questions, okay? There will be simple questions in GATE. If it is your lab exam, in such cases, so there you may get a complex mechanism and there they may ask you to identify the redundant links and so on. Okay? But it's not a lab exam, right? Next item, case 2. This is one case where Kutzbach's criterion fails. Second case, redundant degree of freedom. 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 So what is this redundant degree of freedom, okay? What is this redundant degree of freedom? So whenever I say redundant degree of freedom, so it's redundant degree of freedom, okay? You can see the limits redundant and degree of freedom, redundant degree of freedom. So I can say that degree of freedom will not help you and your mechanism in any way, okay? So we want to have degrees of freedom for a mechanism, okay? If I have degrees of freedom for an entire mechanism, then that mechanism is transforming motion, okay? If a link is having degrees of freedom, so that thing will not help us in any way, okay? So we want to transform the motion. For transforming the motion, we are going for combination of links. Okay, we want degrees of freedom for a mechanism, so not degrees of freedom for individual links inside the mechanism. So redundant degree of freedom is nothing but sometimes there will be some links inside the mechanism which you can move them, but other links will not move inside the mechanism. So if I take a mechanism, generally we have seen some mechanisms like slider crank, 4-bar, 5-bar chains. This is a mechanism. You try to move any one of these links. You try to move any one of these links. If you move any one of these links, other links of the mechanism will be moving. So I can say there is no link which can be moved independently. Okay, there is no redundant degree of freedom. Whenever I say redundant degree of freedom, so you can move some links inside the mechanism independently. Okay, just write down like this: redundant degree of freedom. Redundant degree of freedom. Sometimes a mechanism may have one or more links. A mechanism may have one or more links which can be moved. Sometimes a mechanism may have one or more links which can be moved without imparting motion to other links of the mechanism. Without imparting motion to other links of the mechanism. Sometimes a mechanism may have one or more links which can be moved without moving other links of the mechanism. Such links are said to have a redundant degree of freedom. Okay. So whenever a mechanism having a redundant degree of freedom, we have to subtract those degrees of freedom. Okay. Let's write down like this. For mechanisms with redundant degree of freedom, so degrees of freedom is calculated like this: 3 into n minus 1 minus 2 times lower number of higher pairs minus number of links having redundant degree of freedom. You have to subtract this. Number of links having redundant degree of freedom. So you have to subtract that. Okay. Whenever I say redundant degree of freedom, you can move that link, but other links will not be moving. Okay. Okay. Let's look at this case. This relation is not called as Kurzbach's criterion. So, it's not called as Kurzbach's criterion. If there is no R, that's called as Kurzbach's criterion. Let's look at this mechanism. So, in this mechanism, you can see, so I can move this link, so without giving motion to other links of the mechanism. I can move that link without giving motion to other links of the mechanism. So, if you try to calculate degrees of freedom by using Kurzbach's criterion, so number of links in this case are link number 1, this is link number 2, this is link number 3, this is link number 4. These tubes are welded to link number 2, okay? These tubes are welded to link number 2. It's a single link. The tube and the center thing is a single link. So number of links inside this mechanism are 4. If you try to calculate number of lower pairs, these two are turning pairs and these two are sliding pairs. Total number of lower pairs are 4. 2 turning pairs and 2 sliding pairs. No higher pairs inside this mechanism. If you try to find out degrees of freedom is 3 into n minus 1 minus 2 times number of lower pairs. You will get degrees of freedom as 1. But if you look at this mechanism, there is no relative motion between links, okay? You cannot have any relative motion between the links. So when you try to rotate link number 2, we cannot rotate link number 2, okay? When you try to rotate link number 2, these links will get jammed, okay? The links will get jammed. So because the tubes cannot change their orientation, okay? So if this is the link and the tube orientation is like this, as you rotate this, the tube orientation cannot be changed. So it gets jammed. You cannot have any relative motion. So but if you calculate degrees of freedom by using Kurzbach's criterion, so you will get degrees of freedom as 1, okay? But that is wrong. Degrees of freedom is 0 here if you try to visualize. So degrees of freedom, so for this mechanism, it is 3 into n minus 1. Number of links are 4. 4 minus 1. Number of lower pairs are 4. No higher pairs. There is one link having redundant degree of freedom. That is link 3 is having redundant degree of freedom. So this movement is redundant degree of freedom, okay? So you can move the link, so without giving motion to other links. I can move link number 3 without giving motion to other links. Okay? So degrees of freedom is 0, but you will get it as 1 because of the presence of redundant degree of freedom. Okay? So whenever you calculate degrees of freedom, so first you have to identify, are there any redundant links inside the mechanism? Are there any links with redundant degrees of freedom? And then you have to proceed ahead, okay? If there are any redundant degrees of freedom, this is the procedure. If there are any redundant links, you have to eliminate that link and then you have to calculate effective number of links, effective number of lower pairs and so on. So for redundant degree of freedom, you have to subtract those redundant degrees of freedom. Okay. Try to solve this problem. Gruebler. Link 3 is having redundant degree of freedom. Link 3 is having redundant degree of freedom. I can move link 3 without giving motion to other links. So what's the answer for this? So if you look at this mechanism, in this mechanism there is one redundant degree of freedom, okay? So if I call this is link number 1, this is link number 2, this is also link number 1, so this is 3 and this is 4. So 1, 2, 3, 4, 1. Okay? These are the links. If you look at this link number 3, so link number 3, this link number 4 is connected exactly at the center, okay? Center of the roller. So you can rotate this roller. You can rotate this roller about its center. When you rotate this roller about this center, I can say there will be no motion imparted to link number 4 or there is no motion imparted to link number 2. Are you getting my point? If I exactly rotate about this point, I can just only rotate link number 3 without giving motion to link number 2 and link number 4. So this link 3 is having redundant degree of freedom here. So link 3 is having redundant degree of freedom. You can rotate the roller so without giving motion to other links. So link number 3 is having redundant degree of freedom. So number of links in this case are 4. So number of lower pairs, if you see number of lower pairs, this is one lower pair, second lower pair and third lower pair. 3 turning pairs are there. And if you see number of higher pairs, 2 and 3 are connected by a point contact. And number of links with redundant degree of freedom, R is 1, okay? R is 1 and that is link 3. So this is 9, 6. If link 3 is welded with link 4, so I should not call this as two different links, okay? Then it will be a single link. Then it will be a single link. I just call it as 3 if you weld it, okay? So then also you will get the same answer. So link 3 is having redundant degree of freedom. So whenever there are mechanisms with redundant degree of freedom, so we have to eliminate those links, okay? So link 2 is not redundant degree of freedom, okay? Link 2 is connected with some offset. This is a cam, okay? It is connected with offset, so when you rotate this one, this 4 will be moving, okay? If this was hinged exactly at the center, then this would have been redundant degree of freedom. That's not hinged at the center, okay? That's hinged with some offset, as you can see. If you have a confusion, you make the offset more. Okay? So these are the two cases or special cases of degrees of freedom. So you should keep these points in mind and solve the problems of degrees of freedom, okay? Next, write down like this. Gruebler's criterion. Gruebler's criterion for degrees of freedom of planar mechanisms. Gruebler's criterion for degrees of freedom of planar mechanisms. Gruebler's criterion for degrees of freedom of planar mechanisms. Gruebler's criterion for degrees of freedom of planar mechanisms. So Gruebler's criterion, so we all already seen Kurzbach's criterion. So Kurzbach's criterion is the most generalized equation, okay? So it's valid for both higher and lower pairs. So Kurzbach's criterion we use for calculating degrees of freedom. It is used for both mechanisms with higher and lower pairs. Whereas this Gruebler's criterion so is restricted only for mechanisms which contain only lower pairs, okay? So Gruebler's criterion cannot be used for calculating degrees of freedom for mechanisms with higher pairs, okay? This is only for lower pairs or linkages, okay? So according to Gruebler's criterion, degrees of freedom is 3 into n minus 1 minus 2 times lower pairs. There is no higher pair term, okay? In Gruebler's criterion, there is no higher pair term. Just write down like this, Gruebler's criterion. So valid only for mechanisms. Valid only for mechanisms having lower pairs. Valid only for mechanisms having lower pairs or single degree freedom joints. Valid only for mechanisms having lower pairs or single degree freedom joints. Okay? And rest everything is the same. N is number of links and L is number of lower pairs and so on. So for this mechanism, so if I want to have a mechanism, so or if you want to make any mechanism like this, to make a mechanism, so with 1 degree of freedom. So if you want to make a mechanism with 1 degree of freedom, so this condition should be satisfied. So degrees of freedom is 1, so 3 into n minus 1 minus 2l. Or I say like this is 3n minus 3 minus 2l. 3n minus 2l minus 4 is 0. So I can say like this, if you want to make a mechanism which is having only lower base and whose degrees of freedom is 1, so this condition must be satisfied, okay? Let's write down like this. To make a mechanism with single degree of freedom, the following condition should be satisfied. To make a mechanism having only lower base and 1 degree of freedom, okay? So instead of saying a mechanism with lower base, you just write down linkage. To make a linkage with single degree of freedom, the following condition must be satisfied. This condition must be satisfied if you want to make a mechanism with single degree of freedom. If you look at this condition, so for any value of L, whatever may be the value of L, so I can say this is an even number, okay? For all values of N, that will be an even number. This is a constant and this constant is even number, okay? So I can say like this, if this condition has to be satisfied, this N should be an even number. If N is an odd number, so this entire quantity will be an odd number. These two are even, so you will not get 0, okay? This condition will not be satisfied. So I say like this, to satisfy this condition, this N must be an even number. N must be an even number, okay? So if you want to make a mechanism with single degree of freedom, with only lower base, so N must be an even number, okay? N must be an even number, and if you take even number starts from 2, okay? 2 is the least even number. So with 2 number of links, I cannot make any mechanism, okay? With 2 number of links, I cannot make any mechanism. The next highest number is 4 links. If I take 2 links and you need to fix 1 link, right? If you fix 1 link is only moving, so you cannot transform any kind of motion. So you cannot make any mechanism with 2 number of links, okay? So the next highest number is 4. So the minimum number of links required to make a mechanism are 4, okay? Just write down like this. Minimum number of links required to make a mechanism are 4. Minimum number of links required to make a mechanism are 4. Minimum number of links required to make a mechanism are 4. So minimum 4 links are required, okay, to make a mechanism. So with 4 links we make mechanism. Those mechanisms are called as basic mechanisms, okay? So with minimum number of links. So in our course we have those. So write down 4-bar mechanism. 4-bar mechanism. If we take 4 links and we make a mechanism as a 4-bar mechanism.